Oh, hello again. Welcome to another session of the Learning Class. Today we're going to talk about batteries again. Lithium-ion batteries, the standard of most technology these days. It used to be, batteries are about 200 years old. Lead-acid batteries served had some good service for that long, most of that time. Then other designs came in, nickel metal hydride and such. And then about 30 years ago, Sony commercialized and scaled up lithium-ion batteries. Since then, that has become the standard for pretty much most devices. Lead acid is still important for cars, just the ignition part and other auxiliary systems. And then so lithium-ion is probably going to be the first generation of electric vehicle when that gets widely implemented. So let's talk about an example battery, lithium cobalt oxide. This was the first version of the first design cathode that was commercialized, successfully scaled up, was a lithium cobalt oxide battery. And one way to label this, or one format of specifying what this battery is to have the cathode chemistry. So that's what the cathode is. It's a lithium cobalt oxide crystal. Then you have a dash for the electrolyte. That is LiFeP6N carbonate. That's a general way to write that, to say what that is. You dissolve this powder in some organic solvent, and that's your electrolyte. And then the anode is graphite. So that's the battery we're going to talk about just to begin. And the way that it looks in terms of a electrochemical cell is it has two half cells, the anode and the cathode. So the cathode can be seen as a plate. This is the current collector plate. So if this is the cathode, it will have, for this particular battery, it will have a foam, like a porous film. This is a porous film here. And it has a aluminum current collector, L. And it has a layer, a porous film of this crystal, this lithium cobalt oxide, porous crystalline film. So that's the cathode. Then you have a separator in the middle. Then you have the anode. In some designs, it's a flat plate, two flat plates sandwiched in many different layers of this anode-cathode combination. So this would be the anode. And what that is, this would be a copper current collector. It's kind of like the terminal for each cell, for each combination of half cells, copper, and then on that copper you have a film of graphite. It's a crystalline structure with these specific arrangement of layers. So this would be graphite film, also porous. Then, what this whole thing is for, if this is the separator, what the separator does is it makes sure that only the lithium ions are transported between the anode and the cathode. They can go either way, but if you have this separator, it only allows the cation to go, and then when you only allow this to move back and forth, the way that the cell equilibrates is you force the electron across the circuit. So the electron is forced to go around the circuit. So you're able to cross it across a load. So this would be a load. That's because the separator only allows for cation transport and the electrons go around. So that's what we're doing. We're creating a voltage across here. And then when that voltage is due to this charge, lithium charge, either when it's charged up, it sits on the graphite. When it discharges, it goes back into this lithium crystal lattice. And because of the separator only allowing the protons back and forth, the cations back and forth, the circuit goes in either direction. Because the charge does not equalize here, it equalizes by a circuit instead of just within this electrolyte. Okay, what is the electrolyte? The electrolyte, it's part of this. So the electrolyte is a liquid in the standard in this battery. It's a carbonate liquid, and it's a specific salt that you dissolve in carbonate. Some organic. So that's what it is, and it can conduct the charge left and right, but depending on the current discharge or charging, and the electrons flow around the circuit. So, one thing about this electrolyte is that none of this is an accident. This is all specific materials for many different reasons, mainly due to control the chemical reactions possible. And this is a battery, so these are all electrochemical reactions. It has some coupling with charge transfer, which we leverage to make a circuit that we want. So, this combination of lithium cobalt oxide and graphite has a certain energy level, this natural open circuit voltage, which in this case it's about 3 volts. And the combination of aluminum and lithium cobalt oxide, it's stable. It doesn't do any side reactions within this voltage range. When it gets charged or discharged, the aluminum and cobalt oxide are not going to have a side reaction. That's why we want aluminum. On this side, you want copper because within the discharge and charging voltages, there's not going to be any side reactions. Perhaps if you put aluminum here, there could be some side reactions just because of this possible chemistry that exists between those two materials. This is carbon. It's compatible with copper, meaning that it doesn't have side reactions when it's being charged and discharged. That's why we want copper there. So similar with the electrolyte, we use this particular electrolyte because it can dissolve this lithium and form these cations. That's good for for this charge behavior that we want. And the carbonate doesn't have side reactions, which is good, and it has a voltage window. So if we're going to charge and discharge this battery, if we want a lot of energy, which we do, we need to increase the voltage as much as we can. So the voltage, the higher the voltage we can reach, the more energy we can store. We can go from 0 to some high number of volts. The higher the volts, the more energy. So the window, each of these materials operates within a certain voltage. So this combination of carbon and this graphite and lithium cobalt oxide, that voltage that naturally gets set up by its standard reduction potential and the Nernst equation and the open circuit voltage is about over 3 volts. So this electrolyte is compatible with that because it can also handle about 3 volts. Specifically, voltage window that this can handle is 4.3 electron volts, which is another, it's different than volts, but it's related. And for this, and that's good because you can have more energy. Say, for example, if you were to use water, its window, it's only 1.5 electron volts. So this is less attractive because it has a smaller voltage window, but it's like I said with this, it's compatible. There's no side reactions. This water, it's not compatible. It can have some side reactions with lithium. You can't really use water and lithium. There'd be some side reactions. That's another thing to keep in mind. Water is cheaper and safer, but it's less energy and side reactions. Lithium phosphate fluoride, it's compatible, there's no side reactions, and you can have a higher window. But as long as you keep it away from water, because it's very dangerous for oxygen and water. So that's another safety parameter of this design. Okay, so for real batteries, let's see here. Yeah. So real batteries, there are some considerations to take in mind for real batteries. Because ideally, this graphite, lithium cobalt oxide, anode and cathode combination can give you a certain energy level and an open circuit voltage just based on the materials you are using. That voltage can be used in the circuit. The higher the voltage, the better. But in real life, there are some irreversible losses that you can't really achieve the theoretical limits. It's a loss in voltage that can happen for many reasons. The first one is you have to form the solid electrolyte interphase layer. So you have to form the SEI layer. Any battery, the first step before you can start using it is you have to form, SEI formation is a required manufacturing step. So this is when you're first making the battery, you have to also make this layer. to stabilize, the way that the word used when you stabilize a surface is called passivation. It's the solid surface and the liquid. You passivate that to stabilize the interface. So that's done during manufacturing at the factory, at the manufacturing plant. And if, in class we use the backpack model. In the manual they talk about this, and if you look at the numbers, this formation layer is a very important step. It's part of the cycling, initial cycling. The way how you form it, you just keep on charging it and discharging it, and over time you're going to see, at first you're going to see this really big voltage, but that's a temporary thing, and once you keep on cycling it reaches a stable, consistent voltage. That's because you form this passivation layer. And what that is it would be, see if I have any other colors. It would be that this is the solid anode, the solid cathode I mean. This is the electrolyte. It'll be an additional layer. And this is also required here as well. So this would be the SEI layer. This would be the SEI layer. You need to form those first. And that, once you form those, the voltage is going to be lower than the ideal case. So that's what any real battery, they have to undergo that fabrication step. They have to literally form this layer. Then you can have capacity fade with cycling, meaning charge and discharge. Capacity fade with cycling. Cycling means charge, discharge, charge, discharge, charge, discharge when you're using it. And there's three ways that can happen. It can be the electrode volume cycle. So that's literally a mechanical problem where the electrode takes in lithium ions, and when it takes in lithium ions, it swells up. And then when it discharges those ions, the electrode goes back to its original shape. That's a mechanical stress-strain response, and over time, the mechanical response is fatigue, is one thing that can happen, depending on the specifics of the structure in the process. That mechanical fatigue can happen. Another thing that can happen is you can have electrolyte side reactions, like as we talked about in class, lithium plating or deposition. That depending, if you have a lot of potential across this, in certain cases, if the electrode is too thin and you're trying to get too thick, you're trying to get these force these ions into that bulk of the layer. If there's a big potential drop across there, if it gets too high, you might convert lithium from the ion to a lithium metal on the aluminum. That can happen, and that can ruin the battery or decrease their performance. And another one that can happen is the electrode itself. For some reason, over time, just like It can physically fall apart because this is a powder you start with, and then you use a binder, some glue to glue it together. So that's one thing that can happen. The glue can just degrade over time, or a combination of this, not necessarily fatigue, but the swelling up and down just can ruin the structure a little bit. So there's many reasons why this can decompose. It can also just be from the high voltage. It just can cause some side reactions. So this is a general one, the electrode. And then another one could be what we talked about here, the voltage window. So the electrolyte window is typically smaller than the electrode potentials, just the open circuit voltage from these two, the combination that we have. And so if you were to run this battery, it's designed not to, but if the delta V across the battery, which it's not supposed to, but if you somehow do this, is greater than the electrolyte window, then electrolyte will break down. It's called electrolyte breakdown, and that can be a literal, the molecules in there could literally just break down, or it can cause side reactions and do different things. It'll just be some irreversible loss in performance, maybe catastrophic, some failure of some sort. Okay, so those are some considerations in real batteries that you have to worry about. The theory behind why this works is because carbon has a certain energy chemical potential, lithium cobalt oxide has a certain energy chemical potential, and then when you define some electrochemical reactions that can occur between those, then that gives you this electrochemical potential in terms of open circuit voltage. And that's another way of describing the chemical potential. It's all about, and then the fundamental behavior of that you can frame in terms of equilibrium. If you're saying just by the identity of this material, the identity of this material, it has some chemical potential depending on the reactions you define, that can give you a potential difference or a voltage difference at equilibrium. You're saying if this, at a certain temperature, at a certain concentrations of ions, you can define an energy difference between them. And then you pick a electrolyte that can transport these ions back and forth at the highest voltage you can, depending on this combination. So that's the idea behind the design. But then to get this actual device working, you have to form this SEI layer. You have to worry about how this lasts over time. And then you have to prevent side reactions and breakdown. So those are some considerations. Next, let's talk about Moore theory. So there is some fundamental way to predict or design this design of the battery based on current you would expect. So if we want a high power for this electrochemical device, one way to describe the power is in terms of current going around the circuit, going through the load. That current depends on the reactions going on. So the faster the reaction, the conversion, the Faradaic reactions we're talking about, the faster the current can flow. And there's two situations that can happen. You can have a very fast reaction where these electrons exchange between different oxidized and reduced species, but you can also, and if that's the case, the reaction happens very fast. It could also be possible that even though the reaction is very fast, the electrons cannot move, literally move in and out fast enough. The ions cannot move in and out fast enough. In that case, you're not limited by the chemical reaction, but you're limited by the electron and ion transport. The ion transport is limiting you. And in the opposite case is, if the ion transport is relatively fast, then that's not the problem, that's not your bottleneck. In that case, the bottleneck would be how fast the reaction can happen at the anode and at the cathode. So those are some considerations on current. So the current, so to summarize, the current can be limited by ion transport, or it can be limited by reaction rates. Today, we're going to talk about the case where the electrode is limited by reaction rates. That means that the transport of ions in and out around the circuit is faster, so you don't have to worry about how long that takes. It's limited by the slower thing. In this case, it would be the reaction rates. Okay, so that is what the Butler-Volmer equation is doing. For the Butler-Volmer analysis, it's saying, what is a current? Which is another way of saying, what is the power of this battery? The current, higher the current, the higher the power of this system. Okay, so this is all based on a general reaction where this is the anode, this is the cathode. Depending on whether you're charging or discharging, lithium goes back and forth. And depending on whether you're charging or discharging, the anode material gets reduced or it gets oxidized. Same thing with here. Depending on whether you're charging or discharging, the cathode material gets reduced or gets oxidized. So the net reaction in general that you can write, you would be saying a reduction product at the anode plus the oxidation product at the cathode goes to some oxidation product at the anode plus some reduction product at the cathode. That's a general way to describe what's going on for the whole cell. This is the half cell. I mean, these two are the half cell at the anode, these two are the half cell at the cathode, and it's happening because of charge being transferred. We talked about this net reaction from an equilibrium standpoint using Nernst equation. And so for symmetric, this would be two things. Assuming reaction rate limited, meaning that's the slowest thing. The transport is fast enough, so you're limited by the how fast the reaction is going to happen. And you have equal electron transfer. What that means is, another way of saying that is you have symmetric electrodes. The charge transfer is the same at the anode and the cathode. So under those two assumptions, you can start by defining so-called overpotential. So what from an equilibrium standpoint, you can define these chemical potentials that you can express in terms of energy, or you can express in terms of voltage, because this is electrochemical reactions. So that's an equilibrium behavior, but you can change the speed at which this happens by applying an overpotential. So the overpotential driving, can't spell driving, these are electrochemical reactions, Faradaic reactions. So whenever you, this changes here, the reason why this changes from R to O at the anode is because an electron came on or off. So the current that results in that process is depends on this so-called overpotential eta, which is related to the actual potential of your cell, the voltage you're reading across, minus the equilibrium potential, just by the identity and the concentrations of the anode and cathode. That's what the open circuit. So this is equilibrium, this is Nernst equation. We talked about that before. Okay. So the higher the so basically if you have a certain natural potential, you can induce this circuit to have more potential, and the difference between the equilibrium value and what you apply is the overpotential. So the more overpotential you have, the faster the current. And then when you're doing this reaction, there's an energy barrier to overcome this reaction. So the energy barrier, it's just like the activation energy in standard chemical reactions. An energy barrier for electrochemical reactions would be E. Let's say for the anode, it will be ER. For the cathode, it will be EO. And they're the same. It's a symmetrical system. We can relate that to the number of electrons transferred in this reaction. It's the same, they're symmetrical. And to the overpotential. I'll erase this here. So it's basically the potential here. The energy barrier is given by the potential of this circuit. Then we can relate that to the reaction rate, because of to carry out this reaction, you need to overcome the energy barrier. So it's going to be related to that. So the reaction rate at each surface, what's happening is there's a Faradaic reaction here. The cathode starts off at a certain structure, and then whether you're charging or discharging, an electron will come off or it will come in. And the rate that that happens, let's say that it doesn't matter how long it takes the things to move in and out. Let's say that that's faster, so you only have to worry about the energy barrier effect. So in general, the reaction rate equals the reaction rate at the anode minus the reaction rate at the cathode. And then for this, for reaction rate limited, you can write that this equals R equals some reaction rate constant coefficient at the anode times the concentration of the reduction species, R, times this energy barrier effect. The Boltzmann's constant as usual. So it's this, depending on the temperature and depending on this energy barrier, the rate will increase of the anode reaction. Then the cathode reaction has some rate coefficient, and depending on the concentration of the O species there. And in this case, it's one is a positive voltage, one is a negative voltage, so it'll be a negative activation energy. It's the same magnitude, but it's negative in this cathode reaction. So these are be some rate coefficient. There is both theoretical ways to find this rate coefficient and experimental ways to find this rate coefficient. The concentration of the anodes, the ion concentrations. That's Boltzmann's constant. This is temperature, and this is this energy barrier we're talking about. Okay. So let's draw this here. Let's say that, I'll redraw this here, that E open circuit. So we have a reaction rate at the anode and the cathode. Okay, what about current? If it's reaction rate limited, the current only depends on the reaction rate. The current is the transport of the ions in and out is fast enough that you only have to worry about how fast this is. This is the limiting process. So current I, you can say that I equals the number of electrons you're transferring in the reaction times the area and the reaction rate. This is area of the electrode, the interface where you're transporting electrons and ions back and forth. Then, if you define this I naught, let I naught equal this term related to the number of electrons transferred. CR. So that's some, constant depending on the rate coefficients and the concentrations. Then we can define the Butler-Volmer equation. We can say the current under the reaction rate limited and a symmetric electrodes, you can say that the current is related to this I naught term and these energy barriers. So that's the Butler-Volmer equation. So the current going around, if the electrons are going this way, the current is going this way. That current depends on the overpotential that you're applying and the temperature and this the concentrations. This is also part of the setup there. So under these assumptions, this is the current going through. That's how it's related. Then, when we apply this equation, you can solve for the overpotential. You can describe this in terms of overpotential. So you can say overpotential, if we solve for that, we invert this equation. It's the hyperbolic sine, the inverse of the hyperbolic sine function. That's the equation. And if we plot this, we can see the effect of the overpotential on the current. So if this is overpotential on the y-axis, the x-axis, and the current on the y-axis, this hyperbolic inverse looks like this. So if you have a positive overpotential, you get a negative current. And if you have a negative overpotential, you get a positive current, or the, you know what I mean. And so if this was I1, so the way that what this I naught affects is this. If you were to have a lower I naught, if this is this function with this value of I naught there, and you have this function with I naught there, and if I1 is greater, so as this parameter increases, you get more current. That's how this function works. So that is an idealized, under these assumptions, reaction rate limited in a symmetrical system, you can define the Butler-Volmer equation with this expression here. You can do it for other cases, but this is how this expression looks for the symmetric case, reaction rate limited. You get the current depending on the overpotential and the temperature and the concentrations and rate coefficients. Okay. That's all I had today. We'll continue this another day. Thank you. See you next time.